Consider two concentric conducting spherical shells as shown in the figure. The inner shell has radius A and carries a charge plus Q. Outer shell has radius B, carries the charge minus Q. Let me draw my diagram. Okay. So you have two concentric shells. So half of the region is filled with dielectric material. Okay. So two concentric spherical shells. Okay. So inner one have got charge plus Q. Okay. Outer one have got charge minus Q. Am I right? Speak up. And this is an empty region. This half region is filled with what you call material of, I think he will mention, dielectric having the permittivity epsilon 1. Okay, speak up. Here permittivity means we talk epsilon. Am I right? Speak up. He took that one as epsilon 1 here. Okay, speak up. Here it is epsilon naught. Their permittivity is epsilon 1. Okay, speak up. So the remaining space between the shell filled with the air having the permittivity epsilon naught. That's what he said. Is that okay? This is the configuration. Okay, air here, dielectric here. Okay, air here, dielectric here. He mentioned. Okay, speak up. These are conductors. Okay, plus Q minus Q. These are conductors. Okay, so this is a problem from J.D. Jackson actually. I don't think Griffiths have mentioned any similar problem. Anyway, we shall check. Okay. So this is B here. Okay, outer radius B. Now I will do in one way that is wrong actually. Okay, speak up. You just check where it goes wrong. So what I am thinking is free charge densities, they have spherical symmetry. Am I right? Dot dA bar that's equal to Q free enclosed. Am I right? Speak up. These free charges, okay, they have spherical symmetry. Can I say like this? I will apply this one and I will find D and I will find electric field in these two regions. Isn't it? I mean, if I apply the Gauss kind of law here, if I take Gaussian surface, we are dealing with the region A to B. Okay, speak up. In this region, we are talking about. Okay, not inside the inner one, outside the outer one. Okay, speak up. So D into, can I say, 4 phi r square, that's equal to Q free enclosed. If I take any Gaussian surface here, that's equal to Q here. Okay. So that's why D is equal to Q by 4 phi r square into r cap. Okay, speak up. Then, so in this region, I will take, this is region 1. Okay, this is region 2. Okay, that's better. Okay, so in region 1, okay, D is equal to epsilon naught into E. Speak up. E is equal to 1 by epsilon naught into D, that is Q by 4 phi epsilon naught r square r cap. Okay, in the region 1. So don't write down anything. Okay, you tell me where it went wrong. Okay, so in the region 2, D is equal to epsilon 1 into E. Am I right? Because that's a dielectric, you have dielectric medium over there, isn't it? Speak up. So that's why E is equal to Q by 4 phi epsilon 1 by r square r cap. Okay, speak up. So this is the electric field in this region. This is the electric field in this region. Okay, but it is wrong. Why?
Sir, in dielectric medium, there may be polarization.
So what? This will care only about free charges.
So we have taken D out. D is not constant everywhere.
How do you say D is not constant? Whenever this have a spherical symmetry, I can always apply this one. Am I right? They do not. Free charges do not have spherical symmetry. It is not. I mean, they will not distribute uniform. How can you say that they will distribute uniformly now? Earlier, I mean, when there were no dielectric, you can say, I mean, whatever the charge you give to the spherical surface, I mean, conducting surface, it will distribute uniformly. Charges due to polarization, isn't it? In the dielectric medium, you will have some surface charge in this layer actually, in this layer as well as in this layer. They may push those charges, isn't it? Are you getting my idea? Okay. Once you place that dielectric in the electric field region, they will be polarized. Due to polarization, there will be surface charge definitely appear. I don't know about volume charge. Surface charge definitely appears. Am I right? If you have some dipole moment which aligns along this direction, so in the inner and outer, there will be definitely surface charges. So that's why you are not having a conductor in a charge-free region. Okay, You have a conductor, you have some charges here due to polarization. Speak up. So that's why this Q need not be spherically symmetric. Are you getting my point? So that's why this is wrong. Is that okay?
There are the options.
Hmm?
That is the
One of the option is there. I mean, they will give that one. Okay. I mean, you should check a old gate question. They always give one of the option. If you do any mistake, you will get into that option. You feel like you got the option and you will click that one. Okay. I mean, many students who qualified CSIR net with a very good ranking, they couldn't even qualify gate exam actually at that time. Gate was more easy actually than CSIR. I mean, in lengthy wise, okay, gate questions were less lengthy, but lot of traps. Okay, this is also like that. I mean, I went into that trap actually. Speak up. I quickly thought. I thought of this what do you call free charge carrier. Okay, but I mean, I thought it is spherically symmetric. It is not. Look at that. Okay, because you are not placing conductor in a charge free region. Am I right? You are placing. You have charges due to polarization. Okay, speak up.
So if you have azimuthal symmetry, then we
Huh,
can
huh. You have azimuthal symmetry here. Okay, if you take this axis, speak up. If you take this axis, can I say like this? Hmm? If you take this one as z axis, if you rotate, it has azimuthal symmetry. Hmm? Now, using that azimuthal symmetry, you can find the potential in this region, or at least some proportionality without finding any full constant and all. I mean, potential is constant on this surface, constant on this surface. They are conductors. Okay, even though charge distribution is non-uniform, you can find the potentials on the surface, isn't it? In this region, okay, I mean, Laplace equation is satisfied. You can solve Laplace equation using azimuthal symmetry. I mean, V of r comma theta, whatever we solve. Okay, so one of the author did like that. Okay, potential has azimuthal symmetry. That's why he proved. Okay, using del square v equal to 0. Okay, in the region 1. Okay, in the region 1, del square v equal to 0. It has azimuthal symmetry. He took this one, v of r comma theta, that's equal to summation over al r power l plus bl by r power l plus 1 and all. He proved this potential. Okay, speak up. It is some b by r. Hmm? And corresponding electric field. Okay, speak up. In the region 1, it will be some c by r square r cap. He proved this one. Hmm? I mean, even though you can do this one, okay, it's not a big deal. You just take potential is some constant c here, some constant here. Okay, v equal to I'll take uh, v naught here, v equal to v naught prime here. Okay, speak up. You take potential constant here, you apply your what you call azimuthal symmetry. I mean, if you know the potential at a, potential at b, I think you can somehow prove this one. Okay, you can relate al and bl here somehow. You can prove this one. Okay, speak up. This is one idea. And once electric field in first region, it is c by r square r cap. Okay, speak up. Now look into this interface. Okay, speak up. This interface is radially interface, am I right? Interface between air and dielectric. Okay, that is radial, am I right? That interface is radial here. Speak up. So that's why that radial means, look at here, this electric field itself is radial component, am I right? It has only radial component, no theta component, isn't it? Speak up. So that's why again we have one rule. What is that? Parallel component of the electric field should be continuous, am I right? Speak up. You take parallel you proved that parallel component, I mean, electric field in this region, that is this one, r cap. Okay, so in this region again electric field in this direction, that is r cap only, they should be continuous. And by that we can prove that the same electric field is true in the region 2 also. This is quite hard to accept, isn't it? Electric field is same in the both region. But this boundary condition says, okay, you find electric field in this region. Okay, whatever you got, that is only parallel component. There is no perpendicular component at all. I mean, perpendicular component may suffer discontinuity. I mean, if perpendicular component exists, it is different here, then you would have got different electric field. but you have only radial component of the electric field. That radial component is parallel to the surface. Pick up whatever electric field here, the same electric field here. Speak up. Yeah. No, I mean E1 parallel, E1 parallel is equal to E2 parallel. We have shown, I mean, boundary condition.
So here, if the dielectric medium is not asymmetric and if it's symmetric, like we have it distributed throughout the medium, we don't have epsilon 1 and epsilon naught, and we have epsilon 1 throughout. So then also there will be
No, no.
charges.
When are you filling throughout? That's what you are saying.
Yes, sir.
Then problem is very simple. My idea is also works actually.
So because then the charge distribution will be uniform. They you
Yes,
will have
yes.
symmetry there.
Yes. Then you can apply this one also. When it is symmetric, okay, then whatever induced charge, I mean, sorry, whatever charges due to polarization will also be symmetric. Somehow the whole situation is symmetric. Okay, but here it is not actually. Here it is not spherically symmetric. It has azimuthal symmetry. Okay, he used that azimuthal symmetry idea to prove potential in the first region like this. Okay, when you take the gradient, you will get like this, and again apply boundary condition and prove the same electric field holds here. That's quite hard to. No. Here this Q, because of this polarized surface charge, I mean surface charges due to polarization, they may be pushed or attracted. Okay, so this Q is not distributed uniformly. I mean, it is not spherical symmetry. I'm saying this free charge carrier on the conductor, they are not spherically symmetric. But the whole situation is azimuthal symmetry. A return point. If you rotate like this, okay, it is azimuthal symmetry. You can use that condition actually. Are you getting my idea? I mean, you can define D anywhere. Okay, it need not, you need not to define D only in the dielectric medium. Are you getting my point? You can define D anywhere. Speak up. Is that okay? So there is nothing wrong in defining D. Okay. I mean, look at here. I mean, in the charge free, sorry, in the free space, D is equal to epsilon naught into E. In the space where you have some medium, okay, where you know the dielectric constant, D is equal to epsilon into E. Okay, but I mean, free charges do not have spherical symmetry here. They may have azimuthal symmetry because if you rotate the whole structure like this, you don't find any difference. Speaker. So that's why you can, again, using this one, you prove that electric field is some C by R square R cap in this region, and that R cap is parallel component of the electric field to this interface. Again, use that what you call boundary condition to prove the same electric field holds in the other region also. Is that okay? This is the first argument that you should make. Is that okay? I think Griffiths might have given similar problem outside the chapter. I have to check that out. Okay. Now, what is the next part? Now, you need to find this C, isn't it? In both the region, electric field is equal to this one. Am I right? Pick up. Electric field in first region, that's equal to electric field in second region. Both are equal. That's equal to C by R square R cap. Okay. Pick up. Now, what we do is, speak up. That's why I will take, this is my surface. Okay. I'll apply again this one. D bar dot dA bar is equal to Q free enclosed. Again, you know only free charges, but I don't do like earlier. Okay, we are taking D outside because now D need not be constant on the surface because this Q is not uniform. Okay, but what I will do is I will divide the surface into one portion, this portion, okay, as well, and this portion, a portion of the surface which is in the air, a portion of the surface which is in the medium. Speak up. So when I do like that, okay, look at here. Can I say, so D1 in the first medium into what is the corresponding surface area? Speak up. 2 pi
2 pi
r square plus D2 into 2 pi r square is equal to, I know that is Q plus Q. Total free charge enclosed, that I know. Okay, speak up. Can I say these two are different now? These two are not same. Speak up. Hmm? Because it is not spherical symmetry. So this one is nothing but, can I say, epsilon naught into E1 hmm, into 2 pi r square plus this is epsilon 1 into E2, E2, I'll write same as E1. Okay, speak up. 2 pi r square is equal to Q. Okay, so E1 is equal to E2. You can take that E1 equal to E2 outside, that is C by r square. Am I right? That I can take outside. Okay, speak up. Epsilon naught 2 pi r square, epsilon 1 2 pi x r square. What would happen? Epsilon naught plus epsilon 1 into 2 pi r square. R square got cancelled. C is equal to Q by 2 pi epsilon naught plus epsilon 1. What we have argued? Electric field in region 1 is equal to electric field in region 2 is equal to, speak up, C by r square r cap. Now I found that C. Speak up. What is that one? Q by 2 pi epsilon naught plus epsilon 1. Okay. 1 by r square r cap. Now, I mean, I just wanted to show that these two are equal. And that is 1 by r square r cap. I wanted to show that one. I mean, I should somehow argue, am I right? Something else is happening here. It's not spherical symmetry at all. The whole situation is not spherical symmetry to argue that electric field is along r cap. Speak up. That's why one of the author, I mean, not author, some professor, okay, I mean, they have this Jackson textbook in their course. He first argued using Laplace equation in this region, okay, this one. He first argued this one, okay. Then what he does is, okay, he assumes no volume charges in this region. That I'm not confident enough to say. So saying that no volume charges in this region, how do you say? What he does is he does the same thing in other region. Okay, speak up. I mean, in the second region. Okay, speak up again. Del square V2 equal to 0, and again he proves that V2 is equal to some B dash by R, and E2. Okay, speak up. That's equal to some C dash by R square R cap. Are you clear? He proves this one. Now he apply boundary condition here. He proves C dash equal to C. This is parallel component. He proves that one. But how do you say that there is no charge density in this region? That's my question. He proves like that actually. He says Laplace equation is satisfied in this region. Laplace equation is satisfied in this region. Okay, using our azimuthal symmetry solution. Okay, so he proves this one in the first region. He proves similar. I mean, similar thing should go in this other region because azimuthal symmetry and boundary conditions are same. If you take this is V naught, outer surface, inner surface, V naught dash. Okay, boundary conditions are same. So then he proves this one. Okay, then apply. I mean, then find the electric field. Apply boundary condition. These two should be equal. They are equal so that C equal to C dash. But
How they will be like the same
I mean,
parallel.
yeah, parallel component. Pick up. Hmm.
What I am saying is what from the point you have proved, no sir.
Hmm.
Like E1 is equal to
I mean, I proved like I found electric field here. I said the same electric field followed here. So then I told the same electric field throughout this region. So from that you are saying there is no volume charges. There is no volume charge density because of polarization. Somehow E1 equal to E2. Speak up. That's a bit hard to argue, am I right? Speak up quickly. If you argue that one, next step is very straightforward. This step is nothing actually. D1 not equal to D2, but we know how D is related to E. Okay, speak up. It's all because of this boundary condition only. Okay, that is playing very important role here. Okay, E1, E1 parallel is equal to E2 parallel. That parallel itself is this one. There is no, I mean, if you take this surface interface, That interface is along r cap only, am I right? You have only r cap direction. You don't have any theta cap direction of the electric field.